Hello everyone, welcome back. In this lecture, we shall see fundamentals of internal forced convection. We shall focus our study towards heat transfer in a tube flow. Let us check the theory on internal convection. Classification of heat transfer for internal convection. It can be classified as internal flow, that is flow within the pipes or ducts, and external flow, where the flow over cylindrical surfaces or tubes are considered. In both cases, thermal boundary layer is formed and we have to calculate the heat transfer based on this. There are two surface conditions typically used in heat transfer analysis. The first one is constant wall temperature, that is the temperature will be constant on the wall surface. In the second case, it will be constant heat flux, that is Q will be constant. Okay. Let us check the key parameters and dimensionless numbers. The first one is Reynolds number. As you know, the formula is rho u d by mu, where d is the diameter of the pipe. For laminar flow, the Reynolds number should be less than 2300, and for transition it should be between 2300 to 4000, and for turbulent flows it should be above 4000. In some cases they even mention it should be above 10,000. The next one is Nusselt number, where the Nusselt number is given by h d by k. Here d is the diameter of the pipe, and Prandtl number is given by mu cp by k. The formula is same. Okay. Next we shall see about the entrance region. The region from the tube inlet to the point at which the velocity boundary layer merges at the center line is called hydrodynamic entrance region. If you see in this image for the pipe flow, at the entrance the velocity is uniform from the center to the outer walls. As the flow progresses, the velocity becomes maximum at the center and it becomes zero near the walls. So this is the profile which is formed after certain region, and the profile remains constant beyond this region. So this initial region is called hydrodynamic entrance region. Okay, this is with respect to velocity boundary layer, and next we shall see with respect to temperature boundary layer. The region of flow over which the thermal boundary layer develops and reaches the tube center is called the thermal entrance region. Similar to the previous case, at the inlet the temperature profile is uniform from the center to the outer walls. As the flow progresses, the temperature profile becomes constant. Here the temperature near the walls will be equal to casing temperature or wall temperature, and the temperature at the center will be either higher or lower than the wall temperature depending on the inflow conditions. Okay. So the region beyond the thermal entrance region is called thermally fully developed region, and for the previous case it is called hydrodynamically fully developed region. Okay. The hydrodynamic and thermal entry lengths are given here. L is equal to 0.05 into Reynolds number into D. For laminar case, this is for hydrodynamic entrance region, and for thermal entrance region we have to multiply with Prandtl number. These two are for laminar case, and for the turbulent flow the hydrodynamic entrance length will be approximately equal to thermal entrance length, which is equal to 10d. This is the formula for entry lengths for laminar and turbulent flows. Next, let us check the formula for Nusselt number for internal pipe flows. For fully developed laminar flow, the Nusselt number will be equal to 3.66 in case of constant wall temperature, and Nusselt number will be equal to 4.36 in terms of constant heat flux from the walls. And in case of turbulent flow, the Nusselt number is given as 0.023 into Reynolds number raised to power 0.8 into Prandtl number raised to power n, where n is equal to 0.4 for heating and n is equal to 0.3 for cooling of fluids. So here the Nusselt number formula is same for either constant wall temperature or constant heat flux, but the n will be varying depending on the fluid which is getting heated or cooled. Okay. And this is applicable for Prandtl number between the range 0.7 to 160, and Reynolds number should be greater than 10,000, that is in the turbulent flow region. Okay. Next, let us solve some theoretical problems based on this formula and compare the results with CFD analysis. Thanks for watching the video. I will see you in the next lecture.